So let's say that we have some petrol and we decide to burn it, and that creates us some carbon dioxide and water. My question to you is, if you were to get all of this carbon dioxide and all the water produced, and you were to weigh it somehow. So let's say you burnt 1 kilogram of oil. How many, what would the scale read here? Would it still be a kilogram? It'd be a little bit less than a kilogram. It would weigh 0.9999999 kilograms. That's not because you lost any of the carbon dioxide gas. We're assuming we collect all of the carbon dioxide gas and we weigh it perfectly. The reason why it's not exactly 1 kilogram, the reason why the law of conservation of mass seems to be violated here is because when we burn petrol, we also release energy. And if we recall Einstein's equation, E is equal to mc squared, we know that energy is a form of mass. So that means that when we liberate energy, that's coming from our mass. So where did that 0.00001 kilograms go? It became this energy. That mass was destroyed, completely obliterated. It does not exist anymore. It exists in the form of energy. Now, the way that this relates to binding energy is if we consider the helium nucleus, right? And so we can have a bit of a thought experiment. So let's consider the helium nucleus. We know that the helium nucleus has 2 protons and 2 neutrons. And we're asked to find the mass of it. So you would do 2 times this number and 2 times this number. And the number that you get is 6.695 times 10 to the power of negative 27 kilograms. Cool, right? So if we draw a seesaw, we have 2 protons and we have 2 neutrons. And then on the other side we have a helium nucleus, which is also 2 protons and 2 neutrons. They just bound together. But when you do this, something really weird happens, because this is not the weight. This is not the mass of a helium nucleus. A helium nucleus actually weighs 6.64477 times 10 to the negative 27 kilograms. And so we can see that this number is slightly smaller than this number. So what that means is that this seesaw is not balanced. Actually, it's a bit like this. It's a bit like this. We can see that our actual nucleus weighs less than the sum of its components. What's going on here? This difference in mass that we can calculate here, this difference in mass, which is equal to the difference in mass, which we can see is 0.0503 times 10 to the negative 27 kilograms. This difference in mass, this loss of mass, is the mass defect. So mass defect is the loss in mass of a nucleus compared to its constituent particles. And where did this mass go then? Where did it go? Well, this mass was turned into energy again because of E is equal to mc squared. So because of E is equal to mc squared, we lost a bit of mass. We lost a bit of mass in our in this process of turning our protons into our particles into a nucleus. And this mass defect that's been created, that mass defect that had this loss in mass has turned into energy. Now, this energy is liberated in the reaction. So for example, when you have a nuclear bomb, the massive amounts of energy that's released when it explodes is because some mass is being destroyed and turned into energy. Similarly, when you have a nuclear reactor running, what's happening is that you're destroying some mass. You're destroying some of the mass and turning that into the energy that we use in electricity. So, but to better appreciate this kind of mass defect, we can consider some other ideas. So for example, let me ask you a question. Let's say that there's a man on the earth and he has a pen. Initially the pen's on the ground. The pen's on the ground. And we weigh the system. Right? We weigh the system. Let's say it's 100 kilograms. Obviously the earth would weigh more than 100 kilograms. Let's consider another case now, which is when the man picks up his pen. So he picks up his pen. What will the scale read? It will not be 100. It'll be 100.00000000001 kilograms. Why did it increase? That's a bit weird, right? Why would it increase? Because think about this. When he lifts up the pen, he's increased the GPE, the gravitational potential energy of the system. So if you think about the whole system, the Earth pen system, there is more energy in it now, correct? Because he's lifted it up. There's more potential energy now. And again, via E is equal to mc squared, if you increase the energy, we can see that reflected in the mass of the system as well. So if we were to weigh the system, we can see that it would weigh more because it would reflect the increase in energy of the system. That's pretty crazy. You would actually see it weigh more. Now, students often ask, well, okay, then Bob, is that because the Earth itself began to weigh more, or did the pen get more mass? So interestingly, if you were to weigh the pen and you were to weigh the Earth independently, they would weigh the exact same. But the system as a whole, the whole thing together with the pen and the Earth weighs more. And that's because obviously the gravitational potential energy is inherent to the system. It's not just of the Earth. If you just had Earth with no pen, there's no gravitational potential energy, right? You need these two objects to have GPE. So it's only when you weigh them together. So neither of these particular items gained energy. It's the system that gained energy. Okay, so let's actually see this in action with an example with nuclear fusion. So we recall that fusion is when two atoms come together. Let's say two protons come together. Now, we recall that protons do not naturally want to come together because there's a strong electrostatic repulsion. They're both positive. So how can we get them to come together? Well, that is because of the strong nuclear force. So the strong nuclear force at short distances can overpower the electrostatic repulsion force. And that allows for these guys to come together. Now, if you imagine having two magnets, if you let them they have a force on each other and you let them go, they'll snap together. Similarly, these protons, they will also snap together, right? They'll snap together. And we can see that therefore some energy is being released. So in the process of fusion, so as they come together, energy is released. And that energy, by E is equal to mc squared, if we decrease the energy of the system, we must also decrease the mass of the system. So therefore, that is why the products of nuclear fusion weigh less. If they weigh less, that indicates that they have a mass defect. Let's do the similar thing for nuclear fission. So nuclear fission is a little bit more complicated. If we imagine that we have an atom, So we recall that due to the nuclear strong force, which is attractive between protons and protons, protons and neutrons, and neutrons and neutrons, we're going to have some it's going to be quite lovey-dovey between the nearby atoms, right? So you'll love your neighbors because of this nuclear strong force. But it doesn't work very well. It gets very weak over long distances, right? So for example, this guy, he's going to love his neighbors there, but that's about it. Which means that these two guys, let's say this guy in purple and this guy in purple, they will still feel, they're not going to feel the nuclear strong force attracting each other. They're going to feel the repulsive force due to each other, though, due to the electrostatic repulsion force. So when we have fission, when we kind of let these things kind of break apart, we have them kind of breaking apart here. Then we can see that we're not going to have so much electrostatic repulsion force. We're going to really reduce the energy of the system. So we offer physics, chemistry, and math tutoring. For more insightful explanations like this one, head to tutorgum.com. So because we're at a lower energy, we know that by E is equal to mc squared. If we reduce our energy, the mass will reduce. So that's why also nuclear fission, we can also go to lower energies and we have that mass defect. That's why the products weigh less than our reactants. Now, some students might say, well, okay, so we have less mass now. Is that mass coming from like where did the mass go? Is it like if I weigh each of these protons and neutrons, do they weigh less than normal? No, they weigh the exact same as a normal proton and neutron. It's the system that has less energy, right? Because the system has less energy, the system has less mass. So if you weighed all of these protons together, you took them out and put them on scale and put them back in, you'd see that, okay, that's normal. It weighs as much as I would expect. But when you weigh them together, due to the strong nuclear force binding them all together, and we've reached a lower energy state than before, we let out that energy, means we also lose mass, which reduces the mass that we weigh. Now, I would highly encourage you to check out the next video, which is on binding energy, and kind of elaborate on this concept further. I'll see you there.